And good morning, everybody. Welcome back to Math 105. Plan for today is we are going to start Standard 5, and which will be about how to construct truth tables. And in doing so, we're actually going to start writing sort of our first mathematical proofs to prove when are two mathematical statements logically equivalent. Today I've got office hour this morning at 10 o'clock. Do not have my Monday afternoon office hour because I'm sitting in on another professor's class. Tomorrow I've got office hours from 10 to 11, 1:30 to 2:30. Tomorrow morning, usually Tuesday mornings I have office hours till 11:30, but we have a department meeting at 11 tomorrow, so I can cut that one a little bit short too. And upcoming homework, Standard 4 quiz is due tonight. It's been up on Blackboard and such. Any questions or comments before we get going today? What is the best cure for a bad case of the right angles? Best cure for a bad case of the right angles? The Pythagorean theorem. Okay, so we've now kind of looked at all the different types of statements we're going to be seeing over the course of the semester. We've seen kind of several different forms of compound statements over the last few standards. Statements that have been combined using an and, statements that have been combined using an or. We've also looked at implications, if-then statements. And we've also looked at statements with quantifiers back in Standard 2. And that's kind of all the different statements we're going to be encountering this semester. So in this standard, Standard 5, what we're going to be looking at is, we've kind of talked generally, a little bit informally, about why is the negation of a certain statement have a certain form, let's say. We've talked a little bit about why is the negation of an and statement an or statement, or why is a mathematical state implication logically equivalent to its contrapositive. What we're going to be doing in this standard is looking at kind of a different way of seeing when are two statements equivalent by constructing a table and using the table to look at what are the scenarios under which a statement is said to be true and what are the scenarios under which a statement is said to be false. And by doing that, we are going to basically say, hey, if two statements are true or false at the exact same times in the exact same scenarios, that will be our way of being able to prove that the two statements are logically equivalent. Let's write this down. So truth table is going to be a table used to determine when a statement is true or false, typically a compound statement. And here is the simplest example of a truth table. Typically, when you construct a truth table, you're going to have sort of a header row, where in this case, our header for our simple table is just going to have two statements in it. P and the negation of P. If you look at the simplest statements, which are typically going to be statements of the form P and Q, on the left-hand side, we see a P here. We need to write down all the truth possibilities for that statement, which in this case, we have a simple statement P. The simple statement P can only be one of two things. It can either be true or it can be false. And this is going to sort of be our default column. This is a sort of the column where you're just looking at the original statement or the original statements, and you're just listing out the possibilities for your original statement here. Well, it can be one of two things. It can be true or it can be false. The next column, we're going to list out the next column is not a default column because we can actually fill in this column based on information from the first column. And by that I mean, we could say if statement P is true, what does the negation of P have to be? And if the statement P is false, what does the negation of P have to be? So let's see if we can fill this column in. If we assume that we have a statement P that is true, what can we say about the negation of P?
It's false.
It's going to be false by definition. And similarly, if the original statement P is a false one, what can we say about the negation of P? It's going to be true. So this is going to be one of our default column, where P is either just true or false. And this column is going to be one we can fill in. Based on previous columns. So in other words, when we line this column up here, this negation of P column up next to the P column, what we're really saying is, whenever you just kind of compare, in the circumstance where statement P is true, going to the right, we fill in negation of P in this column based on, well, if P is true, what must negation of P be? False. If P is false, in the column that can be filled in, what can we say about the negation of P? It has to be true. Pretty simple for, I think, for a single statement P. It's a little bit more complicated when you have multiple sort of default columns, when you're starting with multiple statements like a P and a Q, and then you want to try and draw a table that involves compound statements involving the two. So let's see what happens if we make a little bit more complicated table. We can go ahead and put this one in the front page if you're if you're writing in the packet. Let's see what happens when we make a table for P and Q. What are some of the different possibilities for how P and Q can be true and or false? When we just had a single P column, we only had two possibilities. One where P is true, one where P is false. I think we're going to have a few more possibilities now that we're looking at two separate statements, though. What would be some possibilities for P and Q being true and or false?
Both true.
Both true.
Both false.
Both false.
P true and Q false. And P false and Q true.
P false and Q true. Yeah, I think so. And that's going to give us all four of our possibilities. Either both the statements are true, both the statements are false, or one statement is true and the other statement is false, which can occur in two different ways. P true, Q false, or P false, Q true. And this time, these are going to be our default columns. Because now we have two columns that just correspond to the original statements, P and Q. And without knowing what P and Q are, we have to consider all the possibilities for P being true, Q being true, P being false, Q being false. And so for our other columns this time, I'd like to think of what are some compound statements that we can construct using statements P and Q. We've looked at several different ways of combining two statements, P and Q, into a single statement now. What would be an example of one way that we could combine the two? P and Q. Certainly make a column for that. What would be another example of a compound statement involving P and Q?
P or Q.
P or Q. Those are kind of our two standard three ways of using connectives and an or to combine P and Q into a single statement.
if P then Q, or if Q then P.
Yeah. Yeah, we could combine them using an implication. If P, then Q. But now I'm just going to write this one. Don't worry, we're going to see Q implies P later in this practice. I'll show up. And of course, you could also look at, we've already seen how given an implication like if P then Q, how you construct several similar implications. The converse, if Q then P, the inverse, if not P then not Q, as well as the contrapositive, if not Q then not P. And one more that I'd like to look at. P being logically equivalent to Q. Because that's something we could also say is true or false. True if P and Q are logically equivalent. False if P and Q are not logically equivalent. So let's try filling in one of these sort of columns now. And the other 4 columns in this table are going to be ones that we're going to fill in. Let's try and see if we can fill in the P and Q column. And to do that, we just kind of need to go to the left and see if P is true and Q is true. What can we say about P and Q? It's going to be true. What if P is true and Q is false? Yep, and statement's going to be false. How about if P is false and Q is true? And finally, if P and Q are both false. And statement is going to be false. So in other words, in the P and Q column, this is one that we filled in. Actually, all of these are fill-in columns. We see that P and Q is only true in a single row, the row corresponding to the one where P and Q are both individually true. Just like we saw back in Standard 3, if at least one of these 2 statements, P and Q, are false, then P and Q has to be false. Whether it's just one of the 2 individual statements or if it's both. So what I'd like for you all to do now is take a couple minutes and see if you can fill in the rest of this table on your own, using what we've seen from the last couple of standards. You can fill in the columns for P or Q, P implies Q, and P and Q are logically equivalent. Keeping in mind, all of your entries are going to depend on these first 2 columns. What's going on with P and what's going on with Q. So let's take a look at our 3 columns here. So the first column that we haven't filled in is the column for P or Q. Anyone like to take a stab at kind of going down the line and saying how they tried to fill in this column? I saw several of you have some good ideas for writing down entries.
For the first one, it would be true. The second one would also be true. Third one would also be true. Last one would be false.
What do you all think? Yeah, I like it. Corresponding to the fact that P or Q is going to be true if at least one of the two individual statements is true. In the first row, both of P and Q are going to be true. So that would make P or Q true. In the second row, well, there's exactly one of the two statements is true. So the or statement is true. In the third row, exactly one of the two original statements is true. So P or Q is going to be true. And in the last row, both P and Q are false, which is the only circumstance under which the or statement P or Q is going to be false. So unlike the P and Q column, which had true, false, 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 the P or Q column is going to have true, 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 false. How about the implication column? If P, then Q. What did you all think about this one? This one's going to be slightly different from the previous two.
False, true, true.
True, false, true, true? I agree. These were sort of corresponding to the four separate scenarios from our original discussion of implication, where we said the only way for the implication if P then Q to be false, the only way that this implication could be false is if P is true and Q is false. Which means in the P true, Q false row, if P then Q is going to have a false, but it's going to be true in every other circumstance, including even the one where P and Q are both false. The implication, if P then Q, as we talked about last week, is going to be a true one. So, and finally, this last one, which is sort of a new one, we haven't really talked too much about this one yet. P is logically equivalent to Q. Basically saying P and Q have to be the same somehow. Well, how can we fill in that column?
So it's going to be true whenever both of them have the same truth value, false when they don't. So it's true, false, false, true.
True, false, false, true. Questions or comments? Yes?
I just had a question. Couldn't both the statements be true at the same time without them being logically equivalent? Couldn't there be two statements that are true but not necessarily logically equivalent?
That certainly is going to be true if you start getting into scenarios where, like, there's different ways in which a statement can be true and false. Especially, like, if we were to involve quantifiers, then we could certainly have P be true some of the time and false some of the time. Going through this packet, and usually when we go about looking at truth tables, we're going to generally be looking at statements that we can just say are true or false in a single circumstance.
Okay.
So when we talk about P being logically equivalent to Q, certainly there's some times when P can be true and Q false, and maybe under other scenarios, P is false and Q is true. That's a good question, and something I forgot to mention is when we're constructing truth tables, we're only going to be looking at under a single circumstance. Yes, that's a good observation. Glad you made it. And so, Dr. Gerstle, what's the point of this? I like tables. That's the point of this. Also, the real reason we construct these truth tables is because of this fact. If you have two columns that end up being exactly the same, that's going to tell us that the corresponding statements are logically equivalent. Let's write that down. So we're going to say that fill-in columns with the same true or false values will correspond to logically equivalent statements. And so the real reason why we would construct truth tables in the first place is because if you have two compound statements and they happen to be the exact same going down the column in terms of truths and falsehoods, that's going to tell us that they had to correspond to logically equivalent statements to begin with. So if we were to look at these four statements, P and Q, P or Q, if P then Q, P is logically equivalent to Q. Do any of these four columns look the same? It's a little bit tricky because there's a couple, namely these two, that have the same number of truths and falses, but none of them are exactly the same as we go down the line. Even the ones with the same number of truths and falses are true and false at different times. This one has a true, 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 false. This one has a true, false, true, true to it. And so none of these four columns end up giving us the exact same values in the fill-in columns. And so that tells us none of these four statements are logically equivalent to each other. But sometimes you can construct truth tables that have compound statements, like for instance, if P then Q, and if not Q then not P. And if we can show that the columns in that truth table are for things that are, if the columns do come out to be the same thing, that tells us our two statements are going to be logically equivalent. Any kind of questions or comments about this first page? Before we move on to starting to look at some examples where we find columns that are logically equivalent. Okay, let's go to the second page. So the first thing I want to prove is something that we talked about way back in Standard 1. The fact that given a statement P, I claim this. I claim that P, in this case, is logically equivalent to negation of P. If we wanted to take this mathematical statement right here, because this is a mathematical statement, just one written down symbolically, how could we put that in words? How could we describe that colloquially?
P is logically equivalent to the negation of P.
P is logically equivalent to the negation of its negation. Or equivalently, double negatives cancel out. Be a way to do it.
Oh, I was going to say, P
Okay.
is not P.
P is the same as not P. Sure, there can be different ways of saying it. It's our way, this kind of claim is the rule that tells us something like this apple is red would be logically equivalent. If that was our original statement P, what would this claim tell us would be a logically equivalent way of saying the statement, this apple is red?
Sample cannot not be red.
This apple cannot not be red, or this apple is not a color that's not red. Lots of different ways of kind of writing it, but this is saying if you were to introduce a double negative into your statement, it would still be mathematically the same statement. Apple is not a color. Let's say that's not red. So this is what our claim is saying, is that these two statements are logically equivalent. Let's see if we can prove this claim using a truth table. So we need to construct a table, and we're going to need to have two columns, a column for P and a column for not P. And our goal is going to be to show that the truth values for P and the truth values for not P are going to be the same. Meaning we want to show that the P column and the negation of P column are going to logically are going to be the same in terms of when is one true and when is the other one false. So I'm going to give us columns for P, negation of P, and negation of P in order to help us fill in this table. Which of these three columns, how many of these three columns are going to be our default columns, and how many of these are going to be columns that we can fill in based on other information from other columns? Wayne?
Just the P column is the default column?
Yeah, I think just the P is the default, because if we know if P is true or false, that's enough information to tell us exactly how the other two columns should be filled in. Because they're just going to be expressions in terms of P. So here's going to be our default. Just as in the original table that I erased, P can only be one of two things, true or false. If the P column is true, false, what would the column for negation of P look like?
False, true.
That's going to be false, true, because if P is true, negation of P has to be false. If P is false, negation of P has to be true. And now I claim we can fill in negation of P using what we know about negations, that if the original thing is true, the negation has to be false, and if the original thing is false, the negation has to be true. If negation of P is false, what has to be, what do we fill in for negation of P?
True.
Yeah. Since this column is just the negation of the last column, if the last column is false, this column has to be true. And similarly, if the negation of P column is true, what can we fill in about the negation of P column? Oh, sorry. Did a little pencil twirl in the way that made me think you're in your hand.
It's false.
Yeah, it has to be false. Negation of P is false, or blah, blah, blah. Negation of P is true, so negation of that has to be false. Are there any columns in this table that look the same? Which two columns look the same?
P and negation P.
Yeah, it's exactly right. Here, these two columns come out to be exactly the same. The P column and the negation of P column. And so, what that really means is when one of these is true, the other one has to be true. If one of these is false, the other one has to be false under all circumstances. And so that's going to tell us then that since P and negation of P have the same columns, they're true and false under the exact same scenarios. That's our proof that P and not P are logically equivalent. So, what's this? So we can say, since P and negation of P have the same columns, they are true / false under the exact same circumstances. And so are logically equivalent. And that was our first mathematical proof in this course. We showed two mathematical statements are logically equivalent by showing that their columns in the truth table have to come out to be exactly the same. I have a question. Why did we bother making a negation of P column for a single negation? Because that wasn't that wasn't one of the columns that was the same as anything else. What was the purpose, do you think, in constructing a column just for a single negation of P?
Well, it's important because that's one of the steps to get to a negation. You don't just go from P to a double negative. So it's important to take that because you can't just guess that the negation of P is the same as P. We have to prove it by doing that next step in between them.
That's a good way to put it. I agree. That the negation of P itself was not really important at the very end of our proof. And we said, oh, these two columns look the same. But creating the column for just a single negation of P was necessary. It was helpful for us in order to construct what does the column for negation of P look like. And so this is sort of just like kind of a step along the way, a stepping stone in getting from the column for P into the column for negation of P.
Just a quick question. In the future, can we kind of like make that jump? I know in this situation that was the claim, so you can't like assume the claim in a proof. But in the future, can we like jump from, because we know that P is equivalent to the negation of its negation, can we use that as a rule and just kind of skip the middle step in our proof?
Absolutely.
Okay.
Yeah. Once we've shown something in class, and right now we're kind of talking about things we've already talked a lot about informally. Like, I think this is something we talked about on like the third day of classes or something. But it's going to be very true and very useful for us, especially later in the semester when we get to geometry, to say that once we've proven a mathematical statement, we can then just use that statement whenever we want. And we don't need to ever go back and necessarily prove it again, unless I ask you to reprove it on a test or something. But yes, that's a great question and a good point. Once we prove something, we can just use that as a fact from here on out. If we needed negation of P in another truth table, we don't need to necessarily go back through this step first. We can just go right from this to this. So, some of you might be thinking to yourselves, Dr. Gerstle, why did we need, Dr. Gerstle, I kind of see your point about why we needed a negation of P column here, or why it was useful, but come on, I can get from this to this just in my head. Maybe you could have in this case. But there's going to be lots of cases where we construct truth tables with much more complicated statements, particularly once we have both P's and Q's involved. And so in this case, it was not too hard to get from this column or to this column maybe in your head in a single step. But let's see what happens when we try and do the same thing with some more complicated statements. So if you flip to the next page, we're going to look at a couple of our old friends, logical equivalences, that the negation of an and statement is an or statement, the negation of an or statement is an and statement. Except this time I'm giving them a fancy name. Or the fancy name we're going to give them is De Morgan's laws. Where De Morgan's laws are just these things that we've already said back in Standard 3. I just didn't want to overwhelm you at the time by giving them a fancy name. These are the mathematical rules that say the negation of P and Q is the same as saying not P or not Q. And the negation of P or Q is the same as saying not P and not Q. Who do I want to pick? Do you like to prove the and or the or statement as a class? Doesn't matter which. Let's do the and. Okay, so we're going to prove this one using a truth table. So we're going to have to construct a truth table that shows that and in our truth table, we need to show that the column for negation of P and Q is the same as the column for negation of P or negation of Q. That's a bit more complicated and probably something we don't want to do just by constructing those two columns individually. So to start off, what do we need as far as default columns for proving this one? Columns that aren't going to be based on any other column, but ones that are just kind of ones that we need to start with to kick things off, running. Yeah, we're going to need a column for P and a column for Q. Will be our default columns. And as always, whenever we construct whenever we have columns for two different statements, P and Q, that are both default statements, we need to consider all the possibilities for which one is true and the other is false. I like to do that this way, starting off with both true, then just P true, then just Q true, then both false. But this kind of gives us all four possibilities for the two individual statements being true or false. Let's say we wanted to make a column for negation of P and Q. What would be sort of a good intermediate column to put along the way that would help us get from just columns for P and Q individually to a column for negation of P and Q?
And column for P and Q.
A column for P and Q would be helpful because once we have a column for P and Q, we can use that to construct a column for negation of P and Q. Do you have to? Do you feel confident in your ability to make a column for negation of P and Q?
I can just figure out what P and Q is doing and then instantly switch it. As you know, it's just the opposite.
You could. it. But then what you're really doing in your head is you're coming up with a column for P and Q just implicitly.
Yeah, but I don't have to write it down.
I would like for you to write it down just to make it absolutely clear how we go. Just because when you're constructing a truth table, it's best if you show each step individually. Because when we're going from P and Q as individual statements to negation of P and Q, we're really doing two things. We're first combining with an and statement to get P and Q. And second, we're negating that compound statement. So it is really best to come up with columns for both of them, for P and Q, as well as negation of P and Q, even if you feel confident. So P and Q, we already know, is going to be a column that looks like true, false, false, false. That's a column, we came up with that column on the first page, because P and Q is only true if both P and Q are true. So if P and Q is a column that looks like true, false, 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 what would the negation column look like?
False, true, true, true.
False, true, true, true. Just the opposite of the previous column. So here's our negation of P and Q column. We'd like to show that our column for not P or not Q turns out to be the same thing. So before we make a column for not P or not Q, what column or columns would it be helpful to have individually first? As sort of ancillary columns that'll help us to get from P and Q individually to this compound negation.
P or Q?
P or Q? I don't necessarily think P or Q is going to be helpful because we're not ever going to be using the statement P or Q. I sort of like the way you're thinking there, but I don't think that specific one would be individually useful.
Not P on its own and not Q on its own.
I think not P and not Q individually are going to be useful. Because not P and not Q are individually parts of this compound statement, whereas P or Q doesn't really come into play in this at all. Let's make a column for not P and a column for not Q. So not P is just going to be the opposite of the P column. So since the P column is true, true, false, false, the not P column is going to be false, false, true, true. Since the Q column is true, false, true, false, the not Q column is going to be false, true, false, true. And so now we want a column that's a column for not P or not Q. What is that column going to look like? So if not P is false and not Q is false, and if these are false individually, what would be our value for not P or not Q? That one's going to be false since both of the two individual pieces are false. What about if, that's a wimpy F. What about if not P is false and not Q is true? What can we say about not P or not Q? And similarly, if not P is true and not Q is false, the or statement will be true. And if both not P and not Q are true, this or statement, I believe, will be true. There we have it. Negation of P and Q has the exact same column as not P or not Q. They are both false under the scenario where P and Q are both true, and they're true under every other scenario. So we could say, since negation of P and Q and not P or not Q have the same columns, they must be logically equivalent. Where here, unlike in the previous example, where we only needed sort of one intermediate column, here it was helpful to make 3 of them along the way. A column for P and Q to help us to get to negation of P and Q. And it was also helpful to have columns for not P and not Q to help us find when is not P or not Q going to be true. There we go. We just proved De Morgan's first law. Go ahead. I'd like for you all to go ahead and take a few minutes and see if you can construct a truth table to prove De Morgan's second law. The one that says the negation of P or Q is logically equivalent to negation of P and negation of Q. I think we'll be able to use a lot of the same table. Sorry to cut you off a little bit early, but we're a little bit short on time, so I wanted to kind of get through one more example so you have something to look at going for the end of class. We have columns for P and Q already. I'm just going to recycle the same ones we used for the last proof. What would be a useful column to put in that would help us get to a column for negation of P or Q?
P or Q.
The thing that we would get before we take the negation. So P or Q, we've already seen, is going to be true if at least one of the 2 original statements is true. So it's going to have a true, 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 false column. What would the negation of a true, 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 false column end up looking like?
False, 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 true.
Bingo. This is going to be false, 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 true. Our negation of P and negation of Q columns, I think, can look exactly the same. Because they're just going to be the same since we have the same original P and Q columns. But what would the column then look like for not P and not Q based on this not P column and this not Q column?
False, true, true, true.
False, true, true, true?
Or sorry, no, false, 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 true.
As I say, that was our column for our not P or not Q, the first one you said. But for our AND statement, the only way for this AND statement to be true is if both not P and not Q are true. And, you can sort of see again, we have the exact same columns for these 2 statements. So since they have the same columns, we can say they are logically equivalent. Not, the negation of P or Q is in fact logically equivalent to not P and not Q. Okay, that's going to do it for today. When we come back on Wednesday, we are going to look at truth tables for more complicated statements. Well, have a good day. See you all Monday. Hold on a second.
Oh, so. So sorry.
Okay, no worries. This is going to be.
my bad, I should have.
Okay, no worries. I don't make you feel better about
I
it.
didn't even notice. Sorry.
Or it's going to be.
Yeah.
Thanks for class.
Well, thank you.
How are you?
Two.
Thank you. Let's go.